So in this exercise we're going to model oxygen concentration in water. Um, and though this is a primary objective, it's not the only objective of the exercise. It is important to be able to predict the oxygen concentration in water because it's impacted by the most common type of pollution in natural waters, which is organic pollution, typically human or animal waste. From the exercise then, as well as predicting the distribution of oxygen in water, you should be able to explain quantitatively why dissolved oxygen is the single most important parameter of water quality. That does reach across into your human impact course, where you'll be looking at water quality and ecology. But also in this exercise, you should be able to link the mathematics and the actual physical processes that are described by exponential relationships. So you should have a thorough understanding of what an exponential relationship is. And it's very important because they occur in many environmental processes, and you should be able to make the links between this little bit of mathematics and many environmental processes. Now, there's clearly some simplifications involved in this, and a big part of this exercise is to recognize what the assumptions are in the model and what the limitations are, therefore, and what the improvements might be. And they're what you should be thinking about as you go through this. The first part of this then needs to be read in conjunction with the Word document on the action SAG model. And the first part is just to consider the processes that are going on. And we've recognized that there's two processes, one of deoxygenation and one of reaeration. The deoxygenation due to the effluent input, and then the reaeration, which is the natural process of the water being restored. And we've made assumptions, we've thought about it and made assumptions that both these processes are likely to be first order processes. So the deoxygenation will depend on the concentration of the BOD, and the process will be fastest when the BOD concentration is highest, which will be at the start. And the reaeration process also will be dependent on one thing, which is the concentration, the deficit in oxygen concentration. The deficit is the difference between the measured concentration and the maximum concentration that could be in the water as controlled by the temperature, so the oxygen saturation. The first tab, just the processes, where they're described on their own. You have the equations which describe them on the Word document. So we've got the differential equation, which equates the rate of change to the actual BOD concentration for the deoxygenation. It equates it to the BOD concentration multiplied by a rate constant. The integrated form of that is an exponential relationship, which is that the starting BOD concentration is multiplied by e to the negative power of time multiplied by the rate constant. So we can enter that equation. We're starting off with the initial BOD, and we need to make sure all these constants we're referring to have got an absolute reference so we can copy them down. So we've got the starting BOD, and we're going to multiply that by the exponential, so e raised to, it's a decrease, so it's a negative power, and raised to the power of the time, but also multiplied by the rate constant. So we can put e to the minus k. Again, we need to make sure that's got an absolute reference, multiplied by t, which has a relative reference because we'll be copying that down. If we enter that. Okay, and then we can copy that down. Okay, and then we've plotted that. We should look at it and consider, is that what we expected? Well, yes. We started with a BOD of 20. By end of day 1, it's dropped down to 14. And then we've got what clearly looks like an exponential drop. The steepness of the curve is decreasing over time. So the steepness of the curve is decreasing as the concentration decreases. And that fits in words to the equation that we set up, which was that the rate of change of the parameter was equivalent to the concentration of the parameter. So as the concentration of the BOD decreased, then the rate decreased. There is a tab describes exponential relationships in general and goes over these terms in words and has some examples in numbers as well. So you can look at that, but these are actual examples that relate to our oxygen modelling exercise. So similarly, we can look at the reaeration. The reaeration is very similar, but the rate of reaeration is proportional to the difference in concentration between the oxygen concentration measured and the maximum concentration that could be present. The numbers in red, by the way, are numbers that you enter, so they're numbers rather than calculations. So that's what's in red, and we've taken these. This was a typical BOD, 20 milligrams a litre. Here's a typical oxygen concentration. The reaeration is also an exponential relationship because it depends on the oxygen concentration itself. You can work out the equation for that. It's going to depend on oxygen saturation is N10. We need to make sure that we have an absolute reference to that. So N10, and what we're looking at is the reaeration. So it's N10 minus the exponential relationship, which again is N10 multiplied by the exponential minus K times T and we can copy that down, and then we can look at the graph and see, is that what we expected? So we're looking at the oxygen concentration as it reaerates, so it's reaerating from a low value, and the rate of reaeration is quickest to start with, so it's quickest when the oxygen deficit is highest, so that fits with what we think of for a first order process or an exponential relationship. And then as we get closer and closer to the saturation value, the rate slows down. So we've got these two processes. Our assumptions that they're first order processes results in us modelling them using exponential relationships. We can return to those assumptions later on, but that's the mathematics of it, and they seem reasonable. Now in this situation, both of these processes are linked together, so as the deoxygenation changes the oxygen concentration, the reaeration is changing it at the same time. So these two processes have to be linked together, and that means we have this model, which again is described in the spreadsheet. So this is the integrated version of these coupled differential equations here. So we have the two processes, they act together. In the end, we need to integrate them to find out the oxygen concentration or the oxygen deficit at a particular time, and the integration is this. It gives us an analytical solution. It's a first order linear differential equation, and this spreadsheet is just set up to solve that. As we go through the Word document, recognize the parameters that we need to enter into the model. Again, the numbers in red are numbers that you can actually enter, and then there's some calculations in order to make them appropriate for the model. So we're trying to predict the oxygen concentration downstream after the addition of an effluent. First thing we need to do is to predict what the discharge is going to be downstream, because the change in discharge as we go downstream after the effluent's been added will change the concentration of the effluent and the temperature of the water, and both of those things will impact on our reaeration and deoxygenation rate. So the first thing to work out is the discharge, the downstream. So we have upstream, the effluent addition, and then the downstream. So the downstream discharge is simply going to be the addition of the upstream discharge, which is Q is the convention for discharge, it's in meters cubed a day, so it's going to be the addition of this and this. So it's going to be equal to the upstream discharge plus the effluent discharge. So that gives us the total downstream discharge. Now for us to work out the downstream temperature, we need to weight the effluent temperature and the upstream temperature and then add them together. The weighting is going to be weighted by the discharge. Weight the upstream discharge by dividing the upstream discharge by the downstream discharge, and then we can multiply that by the upstream temperature, and then we can put a bracket around that, and that's our weighted upstream temperature. We're going to add it to our weighted effluent temperature, and the weighted effluent temperature is going to be the effluent discharge divided by the downstream discharge, and we multiply that by the effluent temperature, and okay, so the downstream temperature then is going to be 15.7 degrees. We can work out the downstream BOD5, which is measured at 20 degrees, by doing the weighted addition of the upstream BOD5 and the effluent BOD5. So we can do that in the same way by using the ratio of the discharges to weight the BODs. The dissolved oxygen also needs to be calculated downstream. So the missing figure there is the dissolved oxygen at the point where the effluent and the upstream discharges meet. We'll calculate that the same way by weighting the upstream oxygen concentration and the effluent oxygen concentration. The effluent oxygen concentration is 0, and that's the number in red, which is the number that we'd write in, so it's a measured number, so that's 0. But the oxygen concentration for the upstream water is missing from the table. That's because the value's been returned as a percentage saturation. So meters read in milligrams a litre concentration and percentage saturation, and what's been recorded is saturation. So we want to go from knowing the saturation to knowing the actual concentration, and the parameter we need to know in order to do that is the temperature, because the saturation changes with the temperature. And there's a table written in here which is called DO percent saturation for you to see the relationship between oxygen concentration and temperature. This relationship is a curve that's been fitted to experimental data, and it's taken from the Chemical Rubber Industries Handbook, the CRC Handbook, which is a standard source for this kind of information. The oxygen concentration is a fairly complicated function. It's been broken down into pieces to make it less likely to make a mistake in entering it. So it's related to temperature in Kelvin. So the first column is the temperature in Kelvin, temperature in degrees C plus 273.15. And then we have these terms. There's a constant term, and then another arithmetic term related to the temperature. And then we've got a natural logarithm. And then finally, we've got the exponential of the sum of the three terms. It's a relationship that's been derived empirically from fitting a curve to the data. The data then plots up the graph which shows the relationship to temperature, and then there's an example here, and then we've just got an example on its own. If we have an observed 5 milligrams a litre, then the fully saturated water at 25 degrees C would be expected to have 8.14 milligrams a litre, and that means the water is 61% saturated. So that's the observed divided by the expected multiplied by 100. That's saturation. So this table contains the relationship between temperature and oxygen concentration. The way that we're going to use that in the model, we could write the equation into that box. It's quite a long equation to write into a single box, so it's likely to cause problems and there may be mistakes. Also, it's worth understanding how some of these Excel functions work, because you can use them again in similar sorts of exercises. So what we're going to do is to use the Excel function for looking things up in a table. So rather than writing the equation into the box, we're going to use an Excel function to extract the number from the appropriate number from this table. So the appropriate number from this table is going to be the saturation oxygen concentration at a particular temperature, that temperature being the temperature of the water. So in this case, the temperature of the water is the thing that was measured, and it was 15 degrees. And we know where the table is located, which is in this spreadsheet. So the function we're going to use is called VLOOKUP. So it's for finding numbers in a table. So the number we need to look up, what is the saturation concentration of oxygen at 15 degrees. So to do that, we enter the formula VLOOKUP, that's the function, and VLOOKUP then tells you what it does. It looks for a value in the leftmost column of a table, and then returns a value in the same row from a column you specify. So the number we want it to look for is the temperature in the left-hand column. The temperature we want it to look for is 15 degrees, which is E16. And where we want it to look is in this table. And we just need to highlight the table. And then which column do we want it to extract the number from? Well, from this column, the DO saturation column, and that is across, so it's the 6th column. So the temperature's here, column 1, 2, 3, 4, 5, 6. So we tell it we need to extract from the 6th column. If we put true, it will find an approximate match, which is the most appropriate thing, because the measured temperature might not match exactly to the temperatures in the table. The temperatures in the table are resolved at only half a degree. You may resolve the temperature at better resolution than that, and in which case it will find the closest match. If you put false, it would only look for an exact match. So we can close that, and that would return us the saturation oxygen concentration. Now that actually isn't what we want, because we know that we've only got 90% of that. So we need to multiply that by 0.9. So we need to start off by putting in 90 divided by 100. So that's 0.9 times that. And there we go. That's the oxygen concentration that would have been measured if we knew that it was 90% saturated at 15 degrees. And we've used a particular Excel function that's useful in many other situations. Now we can fill in the downstream dissolved oxygen, because we've got the upstream dissolved oxygen worked out. Again, we're just going to weight the dissolved oxygens by the relative discharges. So now we've got the downstream oxygen concentration. Other things we need to attend to, we've got the rate coefficients K1 and K2, but they are measured at 20 degrees, whereas they're actually going to be operating at the temperature of the downstream water, which we've calculated to be 15.7 degrees. So we need to adjust these to make them appropriate to the effluent temperature. And to do that, there's a correction which is dealt with on this tab. The variation in K-factor with temperature fits an exponential relationship. That means that the rate at which the correction factor changes is greatest when the difference between the measured temperature and the standard temperature is greatest. That means that if you were to make a measurement at the standard temperature, which is 20 degrees, then the correction factor would actually evaluate to be 1. So it doesn't actually change the K value. So the K value at standard temperature is 0.34, and the correction factor evaluates to 1. So we multiply it by the correction factor and we still get 0.34. As you go further away from 20 degrees, so if we go down to 0 degrees, then we've got a much bigger difference between the measured and the standard temperatures, and therefore the correction factor is much less than 1. And if we go above 20 degrees, further above 20 degrees we go, the further away from the standard temperature the correction factor gets much bigger than 1. So the formula for the correction factor is the temperature coefficient, C18, raised to the power of the difference between the measured temperature, A20, and the standard temperature, A40. That's that exponential. And then the corrected K value is the one measured at the standard temperature multiplied by the correction factor. The same applies for K2. The correction factor is calculated from temperature constant raised to the power of the difference between the standard temperature and the measured temperature. And you can see that correction factor gets closer and closer to 1 as you get closer to the standard temperature of 20 degrees, and then starts to go further away from 1 as you go past it. And you can note over here and have a look at this that the same kind of correction is operating for variations of electrical conductivity with temperature. We don't use that in the oxygen SAD model, but it's a standard parameter of water quality, and many other temperature corrections follow this exponential. We pointed out for the oxygen it's a more complicated line to fit than just a straight exponential. So back to the model then. We need to correct these, and we could have used the VLOOKUP to pull the numbers from the table, but as the equation's very simple, it's a straightforward exponential, we can just write that in. Look at it. The bit of information you didn't have is this temperature constant, which is 1.135. So we've got the K value at the standard temperature, E32, multiplied by 1.135 raised to the difference between the measured temperature and the standard temperature being 20, so E26 minus 20. And be exactly the same for K2, except that K2 has got a different temperature constant. So the temperature constant for K2 is 1.024. These are all found by experiment. Now the only missing number in order for us to be able to calculate using the model equation is BOD0. Saying it's BOD0 because it's the BOD where the effluent mixes with the water, so it's the starting BOD, and we have the BOD5 on mixing, which is here. So that's the weighted concentration of BOD at the point downstream where the effluent and the upstream waters mix. But we're not going to use that number. The reason being that that's only the BOD5, so that's the BOD after 5 days. What we need to put in there is what the total BOD is. So the BOD after a period so long that oxygen demand has completely depleted to 0. In order for us to calculate that, we can click on this tab for BOD correction. And the BOD correction, the correction again is an exponential. The oxygenation coefficient is 0.34, and we've got a column here that works out the proportion of the total BOD, and it's 1 minus the exponential of the negative deoxygenation coefficient multiplied by time. So e to the minus kt, and it's 1 minus e to the minus kt. You can see that the relationship shows that the rate of oxygen demand is highest to start with, which is when the concentration of BOD is highest. So it's highest to start with, and then it slows down as the BOD decreases, and eventually you've achieved the full BOD. Our measurements are made at 5 days, so you can read up here to 5 days, and if you read across here you can see that 82% of the BOD is used up in 5 days. We're interested in the total BOD, so we know that 0.817 of the BOD is used in 5 days. So if we divide the BOD5 by 0.817, we'll get the BODL. The BODL standing for the BOD last, so the ultimate BOD. Again, we could use a lookup table, so we could use VLOOKUP, but again, because the equation is very simple, we might as well just write the equation in. And we're going to take, so we'll take the BOD5 of the downstream waters and then correct them. We know that BOD5 is about 80%, so we need to correct it so we can get the full BOD. And we can do that by dividing by 1 minus E to the minus K times 5, because it's gone on for 5 days. Okay, so that number we could have pulled from this table. There's a correction factor. We could use VLOOKUP to do that, or we could just write the equation in. And t equals 5 in this case, so it's e to the minus kt. T is 5 for the 5-day BOD. We end up then with our total BOD. And that completes all the numbers that need to feed into the model. And the model, which is written in the box, has been broken down into its pieces here. So we've got t for time, and the first part of the equation is k1 times BOD0 divided by k2 minus k1. And time doesn't feature in that, so the values are the same all the way down. And then the second part is e to the minus k1t minus e to the minus k2t, okay, which you can read there. Now time does feature in that, so it's going to be reading from the leftmost column, so the numbers do change going down there. See the numbers change. And then the third part of the equation is d naught e to the minus k2t. And then we have that d naught, which is the initial oxygen deficit. And then if we put those three components of the equation together, we actually get the oxygen deficit over time. And the oxygen deficit over time is plotted in the graph. So we've got the oxygen deficit worked out against time. Now we're actually interested in how the oxygen deficit changes with distance, and we need to convert then time into distance. And there's clearly assumptions in doing this, but to convert the time into distance we need to know the velocity of the stream. The average downstream cross section has been measured, and we've got that number. We know what the downstream discharge is, which is this number. So if we know the discharge and we know the cross-sectional area, then we can work out the velocity. So given that we've got discharge in meters cubed per day and we've got cross-section in meters squared, then we can work out kilometers per day. So if we divide the discharge in meters cubed per day by the cross-sectional area in meters squared, we end up with meters per day. If we actually want to put it into a more usable number, we should put it into kilometers per hour. So to change from meters per day into kilometers per hour, we just need to divide by 1,000 and also divide by 24. So if we divide by 1,000 times 24, we get 4.83 kilometers an hour. That's the average velocity downstream. And because all of our rate constants for the reaeration and deoxygenation are per day, we should change that number into kilometers per day, multiplying by 24. So 116 kilometers per day. We enter those numbers, then we change the time over here has been turned into distance in kilometers. The time is in days and the distance then is in kilometers if we multiply the time and the distance together. So that means that we can plot the graph of deficit against distance. So we can plot a graph of deficit against distance, and the other thing we might be interested in is considering the oxygen concentration rather than the oxygen deficit. And the oxygen concentration is the difference between the oxygen saturation and the deficit. The oxygen saturation, again, has been taken from the saturation table using VLOOKUP. So the temperature we're interested in, again, is 15.69 degrees, which is E26. The table is on the DO%SAT tab, and it's B3 to G153, and we're looking for the sixth column again, and we get true, so we can take an approximate answer for the temperature, and that gives us 9.68. So the saturation that we'd expect at 15 degrees is 9.688, and we have a deficit of 1.22, so the oxygen saturation is 8.46. So we could change our graph and actually look at, rather than the deficit, the oxygen concentration, and that's our oxygen sag. You can see that the sag actually builds up as you go downstream, and the distance at which it's at its worst is after 2.73 days, or 316 kilometers, in this case 316 kilometers. Now you can find that by looking at the graph that you've drawn, but there's actually a formula which has been entered there as well, which takes you to that directly if you want to find out what the lowest oxygen concentration is and when or where it occurred. Again, the formula is just a rearrangement of the oxygen sag model, but you can see it by just plotting up your graph and see, you can find out exactly where it is.